CPU architecture, before starting about talking about the CPU architecture, one need to look at what are the CPU components and what are the functionalities before anything. So CPU is the most complex component in the computer, mainly because all the processing and all the controlling is mainly carried out by the central processing unit. So however, whatever the operation we do with the computer, it's mainly associated with the program. So CPU, the main functionality of the CPU, central processing unit, is to execute programs. Okay. So these are machine. So these programs are normally run by the computer, which is presented by machine language instructions to the CPU. And what are the main components in the CPU which would carry out the processing of these instructions and the controlling. So there are mainly, we can categorize, we can see 4 components in the CPU. The first one is, as you all know, arithmetic and logic unit, which is responsible for all the calculations and computations and processing of the data. So arithmetic operations and as well as logical operations, shift, bitwise shift operations, all of them are carried out by the ALU. And secondly, the control unit, which is mainly responsible for controlling of the movement of data and instructions into and out of the processor. And also it controls the operation of the arithmetic and logic unit as well. So apart from this, there are other controlling instructions given by the control unit as well. And third component is registers. So we have discussed about registers in other lectures as well. So the register is the most, has the highest speed device in the computer, which can store instructions and data temporarily while instruction is being executed. So this speed is mainly because of the low capacity, and it need to be accessed in the required speed of the processor. So because of that reason, these registers need to function in a very high speed. So they reside in the processor, helping the processor to carry out the processing of instructions. And the internal CPU interconnections help to carry data here and there for the required purposes. So CPU operation. So if you look at the operation of the CPU, what does the CPU do? It always execute programs. So this execution of programs happen in instruction level. Instruction by instruction, these machine language instructions are loaded into the first into the memory and then into particular registers, and then they are decoded, and what function need to be carried out is understood, and that function is carried out and the result is stored. So that process works as a cycle. So one instruction to other sequentially, one by one, these are executed. So what are the main operations that are carried out in executing machine language instruction is firstly fetching the instruction. So in this process, CPU would, if this is the central processing unit, so it would read the instruction from memory, okay? And it would read and keep it in a temporary place, which is called the instruction register, or in short term IR, okay? In IR, it would fetch the instruction and kept temporary until it is taken for the process. And the second one is interpreting instruction. So after getting the instruction into the central processing unit for a register in the central processing unit. So it is interpreted. By interpretation, it's meaning that we are trying to understand what is needed to be done from this particular instruction, piece of instruction. Okay, so the instruction is decoded to determine what action is required. So whether it's an arithmetic and logic operation like addition, subtraction, division, or moving data here and there, or storing event, whatever the instruction is meant to do is understood by the processor from this stage. And nextly, about the fetch data. So to run a particular instruction, we need some data. Not to run, actually execute an instruction. We need some data if that instruction is going to do something with data, okay? So for that, we need to fetch some, as an example, if we get the addition, if you want to add two numbers, we want to fetch the data, fetch those two numbers from memory or an input-output device. So the execution of the instruction is mainly carried out on this execution of instruction, or the action is mainly carried out by on this data. So in this stage, all the data is acquired for the process. And then the next stage is process data. So we would execute an instruction by using the fetch data and the opcode, which is understood at the interpret instruction stage. Okay. So execution of the instruction would require performing some arithmetic or logic operation on the data if the instruction is arithmetic and logic operation related one. Okay. So in processing data, what is happening is normally opcode is applied on the data, something like this. So if you are given some instruction such as add A, B, what you would do is you would add the acquired two data, A and B, and you will, what you are doing is you are adding those two numbers. So that is being done in process data stage. So after processing data, we have a result. So after addition, we now have the added value as the result. So at the end, if we have such value, so we have to write the data in the required place. It may be a memory location or an input-output module. So the result of the execution would be written in either in memory, either into memory, or it will be sent to an input-output module. So now we know CPU components and what is really done in each and every instruction execution. So now let's go components one by one. So firstly, talking about arithmetic and logic unit, it would perform arithmetic and logical operations on data. So as I told you earlier, so integer arithmetic operations which are carried out are the addition, subtraction, multiplication, and division. And the logical operations are AND, NOT, OR, XOR, such operations, and shift or left or right shift bitwise operations. So those are the main arithmetic and logical operations done on data in the ALU. So what is the main process carried out? So it would load data from input registers, and the control unit would tell the arithmetic and logic unit what operation to perform on that data by understood at the interpret instruction stage. And then ALU would store its result into a output register. Okay, so that is actually, so these are the data input and the control input, and it would store its result into output register. Okay, So that's about the arithmetic and logic unit. And about the control unit, it is actually the main controller, which should control the entire operation of the computer. The main responsibilities it has is firstly the maintaining the order and the directing operation of the entire system. And it would control the data flow also between mainly the processor and the other components, including the memory. Those are control signals are required for those data flows. And then it will provide status control and timing signals which is required by the memory and the input-output devices. So, and also it is the main controller of the execution of the instructions as well. So control unit plays a main role in the central processing unit, similarly as the arithmetic and logic unit. More than that, actually, those processors carried out in the ALU are also controlled by the control unit. And then about the registers. So registers are the most powerful, low capacity memory devices contained in the CPU. So in the registers, these registers can be categorized into two main groups: user visible registers and control and status registers. These user visible registers are mainly available for the machine language programmer or the assembly language program. Okay, so that programmer would use them to minimize the main memory references by using these user visible registers. So you don't, if you're a machine language programmer, you don't need to always go and get the data from main memory fields. Rather than you can use the inbuilt, not inbuilt actually, these registers which reside inside the processor. Okay. So some examples for the user visible registers are general purpose registers, data registers, address registers, and condition codes. So secondly about the control and status registers, which are actually not user visible. So these are used by control unit mainly to control the operation of the CPU. Sometimes we need to know the status of a particular function to carry out some control instruction. So that is available by a particular register. So that register is dedicated to show the status of particular process. Okay. So in some machines, so some are user visible, some are not. There's no clear separation in some type of machines. As an example, program counter is user visible in some type of machines, which is a status register. Control it, which is actually a kind of control and status registers. So control and status registers. So there are 4 registers which are essential to instruction execution. They all are considered as control and status registers. So they are employed to control the operation of the CPU. Most of the time, these are not user visible. However, there are some machines use these as user visible as well. So firstly about program counter. So this, we discussed about this in the previous lecture as well in memory architecture, I think. So this program counter is the register in the CPU which should contain the address of an instruction that need to be fetched. Okay. So in simple words, the PC register contains next instruction's address. Okay. And the second one is an instruction register. As in the previous slide also I explained you that the instruction register is used to store the instruction which is fetched from the memory. So if this is the memory, when there's an set of instruction are being executed by the processor, So this instruction would be loaded first to the PC, first to the IR, okay, instruction register. So in IR register, it would contain the most recently fetched instruction. It will be kept for temporarily for a particular time period until it's been interpreted and executed. And third register is memory address register. So it would contain the address of a location in a memory. So memory address registers are actually required to can be used to store an address of a memory location. And the memory buffer register, as the name implies, it works as a buffer. So in this processor, that memory buffer register would contain a word of data to be written to memory, or the word which is most recently read. It works in like a buffer. You get something and you can keep it here until it's been processed. Or after you do the operation, particular operation, as an example, add AB. So you added the two numbers and you have now the result. So until it is been transferred to memory, or before it's been sent to an input-output device, you can keep it here for some time. It's like a buffer, okay? You can keep it waiting for something to be happen. So there are status registers like for sign, 0, carry, equal, overflow, interrupt, enable, disable, or supervisor. So those are some examples for status registers, which would carry out this status information. As an example, if there is an overflow occurred, this overflow register would indicate it from a binary value, binary 1 or binary 0. Overflow happens 1, overflow not happens 0. So that status, whether there's an overflow or not, it's a state. So that is stored in this particular type of registers. Okay. So there are register organizations, different organizations in different machines. So if you look at Pentium 3, register organization is something like this. Okay, it depends on the architecture as well. So you can see here the data registers length is double compared with the register length in this 8086, and the number of registers are also changes from this particular in these three particular types. So now from the beginning, let's have a quick review what we have done. So we firstly discussed about components of the CPU, summarized, and then we discussed about what is happening in each and every instruction execution. So fetching instructions, interpreting instruction, then fetching data, and then after that using the identified code and the data fetched, we would process the data. And then lastly, for the result, we would write that in a particular memory location or a input-output device. So about the arithmetic and logic, so then we discussed about the components in detail, quite detailed, okay? So firstly, we discussed about the arithmetic and logic unit, and then about the control unit, their main functionalities. And then we were talking about registers, which is the most fast and smaller device in the computer. Since there are two main types of registers, as user visible registers and the control and status registers, in user visible registers, we discussed that it is mainly, the purpose is to minimize the main memory references. So the machine language programmer can use them whenever required. Control and status registers, you can see some examples here. So they are not, most of the time they are not user visible. However, there are machines, they are user visible as well. So this register organization differs in different architectures and machines. So some examples are given here. So now if you look at the internal structure of the CPU, so internal CPU interconnections are actually here marked in this picture by using the arrows. So mainly we have internal CPU bus, which should transfer data between various registers and the arithmetic and logic unit. So that is the internal CPU bus. So you can see the arithmetic and logic unit here and the registers here. Okay, so the internal CPU bus would help to communication in between the arithmetic and logic unit and the registers. And the data transfer path and logic control path are also shown here using these arrows. So you can see control paths are marked with ash color and data transfer paths are marked with black color. So about this bus structure, so system bus is the main bus in the CPU, which connects the CPU to the rest of the system. So if you look at carefully, there are three major components of the system bus. The first one is the data bus, and the address bus, and the control bus. Those are the three main system bus components of the system bus. So this is the CPU, which is shown with three main components: ALU, registers, and the control unit. So talking now more about the system bus. So you see the system bus, we transfer data and control signals and address information. So in discussing about the data bus, so you can see in this picture, this data bus and the control bus are bidirectional. Okay, you can send data to both directions, and the control signals also to both. However, address bus only sends, it's unidirectional. You can see it's from CPU to the memory or input-output devices. There's a purpose for that. Let's discuss about that further when we are talking about the data flow in the instruction execution process. So in data bus, it transfers data between main memory and the CPU, and it would have different sizes: 8, 16, 32, or 64. And that's the width, that is actually defines the width of the data bus. When the width increases, you can transfer more data at a single time. So in address bus, it would carry the address of memory locations or input-output device. And if you look at n-bit with the address bus, you would have 2 to the power n addressable words. So each word is assigned a unique address, and it is unidirectional. And the control bus would carry the control information between CPU and the other devices. So in this control bus, it is mainly used to transfer control signals. Mainly the control signals are used to control these data transfers, and also transmit the commands and the timing information to the required components. So that's about the CPU internal structure and main interconnections we have, major interconnections, and what their functionality is. That's what we discussed. So next, about the instruction cycle. So together with all of this information in our mind, we can now look at what is really happening in instruction cycle. So now we know what is the CPU, what are the main components, what are the main responsibilities of the CPU, what are the main functions carried out in instruction execution. So those required facts are now we have discussed. So we can now look at instruction cycle in more detail using the facts we have discussed so far also. So if someone asks you to define the instruction cycle, you can give different definitions. So I will say the time period during which one instruction is fetched from memory and executed when a computer is given an instruction in machine language. So in simpler form, one can say the processing required for single instruction. Okay. So what are the main components in the instruction cycle? So previously we discussed that. What are the main operations carried out? In an instruction cycle, one should fetch the instruction, interpret the instruction, fetch data, and process data and write data. Okay. So all of these things are, why do you say it instruction cycle is in each and every instruction execution, all of these sub-processes are carried out in a cycle. In the first instruction execution, we execute all of this. And when we are carrying out the second instruction execution, we carry out the same set of instruction again, sub tasks here. And when we are executing third instruction, we do the same. So it's circular thing. It's circularly we do the same thing. Okay, so that's why we call it a cycle. So in the simplest form, one can include two sub-cycles to the instruction cycle, which is fetch cycle and execute cycle. Okay, so you would start, when you are starting the instruction cycle, there are many two sub-cycles you can see: fetch and execute, fetch, execute, fetch, execute. Okay, so those are the two basic things we do. It's the simplest form of instruction cycle. Okay, if one asks you to draw the simplest form, you have to include at least these two. So before trying to expand this further, we will just give a review of the registers which are essential to instruction execution. As previously also we discussed this under control and status registers. So here, these four registers are essential to the instruction execution. The first one is the program counter. So as you all know, program counter is used to store the next instruction's address. Okay. So it would contain the address of the instruction to be fetched, or the next instruction's address. It is stored there. So it's a control and status type is control and status registers. So in that type, those are mainly helping for the instruction execution process in the CPU. And the second one is the instruction register. So here, this instruction register is actually the place where you would keep the instruction until it's been executed. So it would contain the most recently fetched instruction, and it will be kept there until it's been processed, identified and processed. So memory address registers is the third one, which contains the address of location in memory. It would contain the address. It is designed to store addresses. So the length and the size and the allocated bits would be enough to store one address in the memory. And the memory buffer register, it would contain a word of data to be written to memory, or the word which is mostly read. So as I told you, it is working as a buffer. So these are the four main registers required for the instruction execution. Since we discussed about the CPU operation, so previously also, so the main functions are fetching, interpreting, fetching data, processing data and writing data. So in fetching and executing, PC would hold the address of the instruction to be fetched next, and then, so if I draw CPU here, so what is first done? So this is the CPU and you have the memory here. And in the memory, these are the set of instructions that you are going to execute, okay? So in the CPU, there's a register called PC, which should hold the next instruction's address, okay? So after each instruction fetch, so after one instruction is fetched, this fetch to IR, so this is the IR register. So this PC is incremented by 1. So that is incremented by 1 when we fetch one instruction to this. So there's an example given. Assume that each instruction occupies one memory word. The PC is set to location 300. Now location 300 is here. So now what would happen is processor will fetch instruction at location 300 in the memory. So this is the location 300 and PC has 300 here. And what to do is PC would, so processor would take the number from the PC register and it would look for that position in the memory. And then it would fetch the instruction at location 300. Then what would happen? So this PC value would be incremented by 1 for the next instruction execution. So like that, it will fetch instruction from locations 301, 302, 300C, likewise because of this increment of using 1, okay? So after fetching the instruction, PC is incremented by 1 each and every time, like that. Then after that, fetched instruction is loaded into instruction register, okay? So after loading the instruction in the instruction register, so the processor would interpret the instruction. That's the next sub-process that happens. So the actions would fall into 4 categories. You should know these 4 categories. Processor, it would be a processor activity between processor and memory, a function between processor and memory, maybe a processor and IO, data processing action, and or a controlling action. So these are the main 4 categories of actions which are carried out by the instructions. Either it would be related to processor, some action of transferring data between a processor and memory, or a processor and input-output device, or maybe addition or subtraction carried out. So those comes under data processing. and it would sometimes be a control instruction. So those are the four main types of actions of instructions. So this execution of instruction involve one or more operands. Okay, give me a second. So these so after we fetch the instruction and after we identify what need to be done by interpreting, so now we need to execute instruction by fetching the operands required. So if it's a data processing action that need to be carried out something like addition, you need to load the operands required for that operation. Okay, so that's the next step. So using these details, one can draw the basic instruction cycle as a state diagram. Okay, so this is called a state diagram. So in this diagram, you can see the states in each and every circles. Okay, so instruction fetch is the first state, and then so first one is the instruction address calculation. So why do we need to calculate the instruction addresses? So this is mainly because, you know, while storing addresses, there are addressing mode, present in the addresses, we have addressing modes. We can use those addressing modes to represent the address. So if you use addressing some complex addressing modes like indirect addressing mode, you may need to do some calculations. Because of that, we have this state here. First, you need to calculate the instruction address if required using the addressing mode. Okay, last week we discussed about addressing modes. So we can calculate the address using an address mode if it uses an addressing mode. And then you can go to the next state of instruction fetching. Now we know the address where the instruction is stored. So then we can fetch the instruction. So after that, after fetching the instruction, we need to look at what need to be carried out. So that is done by the instruction operation decoding. Okay, interpretation is done here. So after decoding, we can find out what operation is need to be carried out. So after identifying the operation, what we need to do next is to fetch the operands. So to fetch the operands, we need to look at where the operands are stored first. Okay. For that, we need to calculate the operand addresses if they are stored using addressing modes. Okay. So operand address calculation is carried out. Then operand fetch is the next state where we would fetch the operands. So here you can see the arrows are bidirectional, mainly because if we have multiple operands, we may have to do this several times, operand fetching. Okay. So then we have to go to the operation. We have to do the operation because now we know what to do and on what to do. Okay. What to do and on what to do. On what to do is what are the operands we know, and what to do is identified here by the decoding process. Okay. So we know what to do and on what to do. No, now we can carry out the operation here. Okay. So after carrying out the data operation, we have the result now of the operation. So what are we going to do with that? Are we going to store the operand? So if you are storing again, you have to do the operand address calculation to find out where are we going to store this data. Okay. So after that, after finding out that if there are multiple results, you have to do this several times, and then you can store the operands. Instruction is complete. Fetch, you can fetch the next instruction. So here also you can see if you go over these arrows like this, starting from here, if you go something like this, this circular, you can come to here. You come from here, you can go here as well as when you are returning first string of vector data. So you are coming to the same place you were. Okay. So this is sorry, this should be like this starting place, up arrow. So it is some circular thing. That's why we call it a cycle. Okay. For each and every instruction, this is a cyclic thing. Okay. For some instructions, some of these status will be null. Some of these status are not carried out. So now we are going to make this instruction cycle in more, give this instruction cycle in more detail. We are going to add some details, more details into this instruction cycle. So let's see how we can do that. We have the most basic cycle here, where the most 5 subprocessors are included. Now we are going to include more and more things in the instruction cycle, which we can use to more give the instruction cycle in a more detailed way. So interrupts are also happening, although we didn't include that into the first figure or the first basic instruction cycle. So interrupts are actually the interruptions which happen to the normal processing of the processor. So there are several interrupt types. Either it would be a program related interrupt, timer related interrupt, input output related interrupt, or hardware failure related interrupt. So the program related interrupts, as the name implies, are generated by some condition that occurs as a result of an instruction execution. Okay, such as arithmetic overflow, division by 0. So those are the examples. So so we ask the computer to do operations now, and set of instructions now. If some instruction asks to divide the number by 0, what would happen? It would stop there. Okay, it is some kind of interruption that can happen while we are carrying out the instruction execution. And the timer related interrupts are generated by the timer in the processor. It would allow the operating systems to do some functions in regular basis, maybe an update likewise. And IO related interrupt, input output related interrupts are generated by the IO control mainly to signal normal completion of an operation or to signal a error condition. Okay. So that's input output related interrupt. Because of the input outputs are not happening properly, so we can't proceed because of that. And the hardware failure related interrupts are normally generated by the failures associated with hardware, like a power failure or a memory parity error, something like that. So because of that reason, we can't go further beyond that point. We are stuck there. Okay, so that's the interrupt. So those interrupts need to be handled So we have to stop what we were doing. We have to go to the interrupt handling set of instructions that need to be carried out to interrupt handling, and then come back to the previous position. So in interrupt cycle, what is happening is actually a processor would check if any interrupts are occurred continuously. Okay, so this is normally identified by interrupt signal. So if there's an interrupt signal, that means there's an interrupt happened. So we need to first address the interrupt and then come back to where we were in our instruction execution process. So if there are no interrupts are pending, the processor will proceed the fetch cycle and fetch the next instruction of the current program. If it is, if there's an interrupt, you would have to go to interrupt handling route and then come back to the place where you were. Okay. So what is happening in detail is when there's an interrupt, it would, so assume that we are executing a program like this. Okay. That's the program in the memory. And this is the CPU. So, so now CPU identified that there's an interrupt happening. Okay. So so assume that we were executing the third instruction. So the third instruction is fetched to the instruction register. So one by one, it is being executed by the processor. So it will suspend the operation of current program execution. So it will stop here. Okay, it would not go beyond here. It has come from here to here and it stopped there. Okay. And it will save the contents like address of the next instruction and data about the current activity. So those would be stored in the memory mainly because we need to come back after handling this interrupt. When we are coming back, we should facilitate the next instruction to run. So after we save all the required information, it would set the program counter to the starting address of an interrupt handler routing. Okay, this is nicely shown in this picture. So you can see the user program. So this program is executed by the processor one by one. One instruction is fetched and decoded, executed, then the result is stored, and go back and take the second instruction. It is decoded and then executed with using the fetch data, and then again after storing the result, it will move to the next instruction. So likewise, each and every instruction is executed. Okay. The instructions are executed up to this point. However, at ith instruction execution, there is an overflow happens. Okay. So that's a kind of program interruption. So then we have to go to the interrupt handler. Before going to the interrupt handler, we should save the current PC value. So what is the PC value? This PC would hold the next instruction address. So it means I+1. That PC value should be stored in the memory. So it would be stored in the memory, and all the other information required to restart work from I+1 need to be stored. Okay. And then we go to the interrupt handler. So after saving the required information in another place, we go to the interrupt handler program. So in the interrupt handler program, we have instructions given to handle that interrupt. tackle that interrupt, and then we can come back to the next instruction. So when you are coming back, we require to find which place are we going to start from again. So it is obviously I+1. However, it need to be, so previously we stored that value in the memory. So we will come back to the particular place, and then we would restart doing the previous user program from that location. Okay, we are not going to go to 1 because this location is stored in the memory. So those are the main steps carried out at the interrupt cycle. So, so let's see whether we can include this interrupt cycle also in the instruction cycle. So if so, where are we going to include it to? So interrupt is an interruption of the normal sequence of execution. So when the interrupt is being completed, the execution was resumed in this way. So to accommodate interrupts, an interrupt cycle is added to the instruction cycle. So we'll start here, and you can see the basic 2 cycles which we discussed earlier. And then at the end, we can add check for interrupt. It's again checking whether there's an interrupt each and every time after an instruction execution. So if there's an interrupt, we have to go and handle that interrupt in the interrupt cycle, and then go to the next instruction, fetch, after handling the interrupt and coming back. So now we have 3 sub-cycles. What are they? Fetch cycle, execution cycle, and interrupt cycle. So those are the main sub-cycles which we have now in our instruction cycle. And now can we include these interruptions into the state diagram as well? So this is the state diagram. So, so once the instruction address is calculated and the instruction is fetched, then we move to the operand fetching part, which has 3 components. So not 3 components, actually 2 components: operand address calculation and operand fetching. So this would be carried out several times if there are more than 1 operand need to be fetched. Then after that, we have the operands with us, and we know the operator. So we will apply the operator on the operands in this state. Then again, we need to store the operand. So we will calculate where we are going to store the operand is. And then after that, we can include interrupt check state similarly as here. Then if there is an interrupt, you have to handle the interrupt and go back to the next instruction fetch state. So that's the instruction cycle together with 3 sub-cycles: fetch, execute, and interrupt. And now we are going to add another sub-cycle, which is the indirect cycle. So this indirect cycle is mainly related with the indirect address. Okay. So previously in addressing modes, we discussed that there is an indirect addressing mode where the address is not directly stated in the instruction. So we have to go to a particular location in the memory and fetch the instruction address from there. Okay. So in this indirect cycle, what we are doing is we would do one more memory access and find the real address or the effective address from that place. So now we are going to add that also to this instruction cycle. So you can see in this picture, it's shown how the interrupt is included here after execution. And after each fetching, we can see if there is an indirection done, address that indirection by using a memory access. So after instruction is being fetched, it is examined to determine if there's any indirect addressing is in or not. So if there's indirect addressing, we have to get the required operands using the indirect addressing mode. So can we include that into our state diagram as well? So this is called the block diagram and this is called the state diagram. Okay, keep that in the mind. So this would show the states in detail one by one. Rather than that is more summarized, which would show blocks. More information is summarized compared with this detailed state diagram. So in this state diagram, you can see now there are 4 subcycles. Previously we had fetch, execution and interrupt. Now we have added indirection as well. Indirection is only added as operand fetch and operand storing situations because it is related with the addressing. Okay. So indirection is marked with the circular arrow like this. So now we have discussed about the instruction cycle in detail. What are the basic sub-cycles? Fetch cycle, execution cycle, interrupt cycle and indirect cycle. So, now up to now we have identified how we can represent the instruction cycle together with this detailed component and 4 sub-cycles. Okay, so that's what we have done so far. So we know now how the instruction cycle is being carried out. However, we can specifically look at how the data flows while these sub-cycles are carried out in an instruction cycle. So that is, we are going to do it with this. We are going to do it next. So now we are going to look at how the data flows in between memory and the CPU. So we are going to look at how the data flows in between memory and the CPU using this system bus. Okay. So that's what we are going to do here. So the exact sequence of events during an instruction cycle depends on the design of the CPU. So we assume that our CPU would have these registers PC, MAR, IR and MBR. Those are the 4 registers we assume that the CPU has. It should help for the execution of these instructions. So PC is the program counter, which should hold the next instruction address, and MAR is the memory address register, which we can hold memory address there. And IR is the instruction register, which we use to store instructions. And MBR is the memory buffer register, which acts as a buffer where we can keep some data for a particular time period until it's been used. Or so if it is a result, we can keep in that buffer some time until it's been written into the memory or input-output device. So now we are going to look at fetch cycle. What is really happening in the fetch cycle? In the data flow level, what is flowing? How is this fetch process happens? Okay, so that is discussed in this slide. So first of all, we know PC, what does it contain? It holds the next instruction address. So now we are going to fetch the address first. So the address is moved to MAR and placed in the address bus. So by the program counter, we would identify from where we are going to fetch the address from. Not the address, instruction from. Okay. PC contains the address information of the next instruction. So we now, by looking at the value in the PC, identify in this data location, there is the next address, next instruction address. Okay. Next instruction is, so using this address, we go to that location, and we need to go to that location and fetch the instruction. So how does the data flows in this process is discussed here. So we know in PC we have the address of the next instruction. That address is firstly moved to MAR. Okay, it is moved to MAR, which is the address register where addresses can be held. Okay, and then it will be placed into the address bus. And then it will be placed into the address bus. So this is to fetch the instruction. Okay, and so after you place that here, so without control signals, you can do nothing. So control unit should request a memory read. So control unit is request in a memory read using the control bus. Okay, so it would request a memory read. So the result would be placed in the data bus. So the result would be placed in the data bus and copied to the MBR. So now it is going to MBR, memory buffer register. Okay, the result. And then move to IR. So buffer is a place where it is kept until it's been moved. As you can see. So now you can see how the instruction is being fetched in this process. So from PC, we identify the place where we need to access now to fetch the instruction. And then the PC program counter's address is moved to MAR. And after moving that to MAR, that address is taken to memory using this address bus. And the resultant content of the memory location is taken to this MBR using the data bus. Okay, this way. And then it is moving to IR. Now instruction is fetched. Instruction is fetched to the instruction register. So using these processors, we fetch the instruction. So this figure would, in summarizing, it would it would show the data flow in the fetch cycle, fetch instruction cycle. Okay. Fetch cycle is one of the sub-cycles in the instruction cycle. And data flow in the indirect cycle. So how the data flows in the indirect cycle is discussed here. So once you finish the fetch cycle, the control unit need to examine the content of the instruction register. So if it contains an operand using an indirect addressing, you need to carry out the indirect cycle. Okay, so this is how it is carried out. The rightmost n bits of the MBR, which contain the address reference, are transferred to MAR. Okay, so here to here, you can see this arrow indicate that transferring. So it is being transferred from MBR to MA. So after that, control unit need to request a memory read, and it would get the desired address of the operand into MBR, again the temporary buffer location where you can store values temporary. So the control unit would request a memory read to get the desired address of the operand into the MAR. Control input it's a control signal here. So you can see so after that to get the desired address of the operand into the MAR. So you get that address from memory. Okay. So why do you get that address from memory? What is happening in indirect cycle? In indirection. So if this is the memory and if this is the instruction, so this is the memory. So in indirect cycle, so the data address mode we use is the indirect addressing mode. So the address is not directly given in the instruction. Rather than that, we are given an address where we have to go to the address, and the real address we need to fetch data is stored here. Okay. So what we do is we go to the particular address mentioned in this place, and then we go to that place and take the stored value. Okay. So control unit would request a memory read to get the desired address of the operand into MBR. So after identifying which address we are going to get the data from, or the real address of the data which we are going to use, you have to use that, and you have to fetch that address into the processor. So that's what is carried out here. And the execute cycle is the third main cycle. So how does the data flow in this sub-cycle? So in the execute cycle, there's no diagram given here, mainly because there are different types of actions are being carried out. So because of that reason, there's no detailed information is given here, because if you write, it is specific from one activity to other. So collectively you can see the execute cycle would take carry out the function specified in the instruction. Okay. This cycle may involve either transferring of data among registers or read and write from memory, and or the invocation of ALU to carry out certain function specified in the instruction. That is what is done in execute cycle. And the fourth sub-cycle we were talking is interrupt cycle. So what is done in interrupt cycle is we have to hold the current operation of the set of instruction we were carrying out, and then go to the interrupt handling route and carry out the operation specified in that interrupt handling program, and then come back. So that is data flow, how data flow is mentioned here. So first we have to copy the content of the PC. So this is mainly because we can resume the normal activity after we resolve the interrupt. So the content of the PC are transferred to MBR. So you can see PC content transferred to MBR. So that is mainly to put it into memory, to be written to the memory using the data bus. You can, so now PC's content is transferred to MBR, and from MBR to data bus, and from data bus to memory. Okay. And then a special memory location reserved for this purpose is loaded into MAR from the control unit. As an example, stack pointer. And then the PC is loaded with the address of the interrupt routing. And it can now carry out the interrupt handling routing, okay? Interrupt handling route should be handled. The next instruction cycle then would begin by fetching the appropriate instruction. This happens after interrupt is being handled. So that's how data flows in the interrupt cycle. So far we have looked at the data flow of several subcycles, which is firstly about the fetch process, what is happening in the fetch cycle, and then about indirect cycle. So if the operands are stored using indirect memory, addressing mode. So if it use the indirect addressing mode, so this is how the data flows and do the fetching process of the operands after calculating the address of the memory location where they are stored in. And then we talked about the execute cycle, which is quite specific from operation to operation. And then about the interrupt cycle and how the interrupts are being handled and carried out. So those are the main 4 sub-cycles which we discussed so far. Okay, now we are moving to our next topic, which is a way of accelerating the processes discussed so far, which is happening in the process, which is instruction pipelining. So if you look at the CPU performance, as we always discussed in the previous lectures as well, so about this memory and speed of memory access and the speed of the CPU, central processing unit, they are very, they have a very big difference, okay? So to further smooth the functionality of the instruction execution process, you can use these enhancements, okay? You can improve CPU performance by carrying out these enhancements. One of the enhancement is instruction pipelining, which is marked here with the red color, okay? So that's what we are going to discuss today. Apart from that, we can use a cache memory, okay? So we discussed about this earlier as well. So how can you improve the CPU performance? By using a cache memory. How can you do that? So you know this memory bottleneck. So memories cannot be fed in the required speed from the CPU. So as an alternative, we sit another memory device in between this CPU and the main memory, so that frequently access data items and nearby data items for a frequently accessed items are stored there, okay? So it's something like this. So when you are cooking, assume that you are going to cook in the morning. So early morning, every day you are cooking your meal. So when you're cooking your meal, after you cook for several days, you understand that you need the knife, okay? So the knife is far away. So it's better to keep the knife near to your cutting board, okay? So you arrange some place to keep that. Okay, so after some time you I understand that salt is required to put into every curry. Okay? So there is something frequently accessed. So you keep that there. So cache is such place where the most frequently accessed items are stored for fast accessing. Okay. So the CPU, when it requires accessing these frequently used items, it doesn't need to go to the main memory. Rather than going to the main memory, it can go to the cache. It can go to the cache and do the operation quite faster. Okay? So that's why we use a cache memory there. And then we can use multiple registers rather than a single accumulator to improve the CPU performance. So what is meaning by the first point? Multiple registers rather than a single accumulator. So what's the purpose of accumulator? So assume this is the processor. So in the processor, we have different registers, set of registers, isn't it? So accumulator is the register where you can keep some value to be used for the next operation. Okay. So rather than using a single accumulator to keep one operand until it's been processed, or carried out the operation with this operand, we can use several. So then you can keep several more operand values to be used. So in that way also we can make the process faster. Okay, so the main target is to make the process faster. Okay, so by this, I think now it's clear for you how you can improve the speed using these two main processes. So the third one is instruction pipeline, which we are going to discuss next. So rather than instruction pipelining, let's discuss about pipelining. So what is pipeline? So as an example, if we get the assembly line in a manufacturing plant, products would go through various stages of production. So as an example, so here you can see the Toyota assembly line, which consists of robots. Okay. So in this pipeline, you can see several robots are specified for several functions. Okay. Not all the robots know everything. Okay. So that's why we have a pipeline. In this pipeline, some robots are collecting the, putting the engine parts. Some robots are fixing the lights. Some robots are spraying ink. Likewise, there are specific tasks for each and every robot in the pipeline. Okay. New cars are going from one end and the other cars are accepted from the other end. So this some parallel process is being carried out and not like this, like there's a single car coming, all the processes carried out, and then it's sent out of the plant. And then the next process is accepted, all the works are carried out, and then finally car is going out from the plant. It's not something like that. It's like parallelly each and every car is accepted within the capacity of the plant, and then the works are carried out parallelly. Okay, so that's the behavior of a pipeline. So you can see mainly these are the keywords. Various stages are worked simultaneously, are carried out simultaneously. Okay. Okay, so let's see whether we can apply this pipeline principle to instruction execution. Okay. So in a pipeline, new inputs are accepted at one end, and before the previously accepted input appears outputs at the other end. Okay, there's a parallel processing is being done. So if you compare this with instruction execution process, do we have opportunity for pipelining? Do we have a set of stages like in car manufacturing? Firstly, the hardware or the body of the car is prepared. So that is one stage. And then engine is placed is the second stage. Likewise, can you see some distinct stages in instruction cycle? Yes, we can see. So we have done that. We could see several cycles, execution like fetch cycle, interrupt cycle, indirect cycle. Likewise, we could see some stages, and those so there's we see there's some possibility to do it as an pipeline. Okay, so there are two distinct phases. Basically, in the most simplest case of a cycle, instruction cycle, we discussed only about two cycles: instruction fetch cycle and the execution cycle. Okay, so we can again look at those two phases first. Okay, so in execution of program, it is actually carrying out set of fetches and set of executions. Okay. So here you can see how the instruction is fed, and so that is fetched in the fetch cycle, and then the instruction is executed and result is outputted. So, so can we do this in parallel? So to do this in parallel, we need to have some waiting time of one process until the second one is carried out. So if you look at this, after you finish the fetch cycle and until you finish the execute cycle, next instruction is not being fetched. The fetch box waits until this execution completes. Okay? So because of this waiting, we can occupy this fetching process to the next instruction. Okay, in simple words, now we have parallelized. Until the first instruction is being executed, the second instruction can be fetched. So this is called the two-stage pipeline, which we can define using instruction fetching and execution. So for simplicity, we assume that fetch step of any instruction can be completed in one clock cycle, and the execution step is also can you complete it in one clock cycle, which is not true. So we assume to understand the process. So now we can define, or we can write down the steps of the operation of the computer as given here. Okay. So we assume that in the first cycle, the fetch unit fetches the instruction. Okay. The fetching process happens in the first clock cycle. And in the second clock cycle, the instruction fetch unit would proceed with the fetch operation of instruction. Okay. And thirdly, meanwhile, the execution unit do the operation, you can do the fetching of the next instruction. Okay. So two-stage pipeline is drawn here. As you can see, instruction fetch unit is here, and you can see the stage of the buffer here, and the execution unit, storage buffer here. So F1 and E1 in this picture refers to F for fetching and E for execution. 1 refers to the first instruction, 2 refers to the next instruction likewise. So execution of a program consists of a sequence of fetch and execute steps given here. So you can see now how it has been parallelized. So when the first instruction is fetched, you can't do anything. So after it is fetched and in the execution process, you can parallelly start fetching of the second instruction. Okay. And then the second instruction is, after the second instruction is fetched, you can start execution of that, and parallelly you can fetch the third instruction. So likewise, this process is now parallelized. You can see, so if you put these boxes one after the other, it would take quite a lot of time. F1, E1, F2, E2 likewise. Okay. However, now we have parallelized it in this way so that we can save some time. So the effectiveness of this two-stage pipeline is, so if the fetch and execute stages were equal duration, instruction cycle time can be halved, but fetch time usually is shorter than the executed time. Okay, any jump or branch statement means that free fetch instructions are not the required instructions. So here you can see it is go sequential fetching. First instruction is fetched and the second instruction is fetched next, and the third instruction is fetched after that. Likewise, sequential execution. However, that is not the case always. So if there is a loop or iteration, so you may have to do the first instruction over and over. Okay. So in that case, there's a problem. So can we further reduce the time? Can we further reduce time and save time? Can make this process faster? So for that, we can add more stages to improve the performance. We can fetch instructions. Then we can decode the instruction and calculate operand. Likewise, we can divide the two-stage pipeline into six-stage pipeline. 1, 2, 3, 4, 5, 6. Now there are 6 stages, you can see. So rather than having 2 stages, we can have 6 stages as given here. So we have subdivided the previous stages into more detail. Okay. So this is the 6-stage pipeline. So you can see now we have further improved we have reduced now time wastage, because you can see we have further divided one stage into several further sub stages. So this is the picture of the 6-stage pipeline, where parallelly we can execute instructions and save time. So the assumption of this 6-stage pipeline is equal duration for the stages, and each instruction would go through all 6 stages of the pipeline, which is not something that would happen. And we would load instructions that does not need WO stage. So we may not need to write results always. And FI, FO and WO stages involve memory access. So sometimes we may not be able to do them in parallel. These are the assumptions, okay. On these assumptions, we can assume that this would happen. So there are no memory conflicts, so access can occur simultaneously. So once you have accessed the memory, you have to wait until that access is over to access the memory. Next, access the memory. You can parallelly access the memory. In most systems, this is not permitted 6-stage pipeline. How pipelining is one of the mechanisms you can use to improve the CPU performance. So from here, we finish the content which are planned for this subject. So since we have 40 minutes, I thought I would ask you to do a past paper question from this section. We can, previous day we did this exercise. So I stop my share. And please wait until I